continuing with the factors which affect the overall performance of a network, it is also important that we consider the oft ignored aspect, which is called the accuracy. The accuracy of the network is being defined here, and then we are going to look at the factors which affect accuracy. Before we start, let's agree on the definition of accuracy not being precise. Let's look at this figure. As you can see here, there are 4 scenarios given in which there is a target with the bullseye given as the innermost circle, and then there are certain hits or shots on it. As you can see here, the right top circle you see on this particular target, the system has low accuracy but high precision. It actually means that none of the hits is in the bullseye, but all the hits are clustered together. On the left top, you see that it is a low accuracy system with low precision. All the hits are scattered around the bullseye. On bottom left, you see that the system has high accuracy but low precision. Why do we see that? Because we see that there are some hits within the bullseye, but not all are in the bullseye. And on the right bottom, we see the most desirable system, of course, which is highly accurate as well as highly precise. Here, we see that all the hits are in the bullseye and they are clustered together. So, with accuracy, what we mean is that the system shows desirable performance. Formal definition of accuracy in terms of networks would be that the data sent and received should be the same. Alternatively speaking, it is actually the number of error-free frames transmitted to the total number of frames transmitted. Of course, if there were no error-based frames, the transmissions of useful transmissions would be exactly same as the total transmissions. The factors which affect accuracy include lot many details. To begin with, let's look at the effect of routers. The router processes incoming packets, it might reorder them. At the physical layer, the effect of spikes or power surges cannot be ignored. And as an example, look at the scenario in which there is a 10 megabits per second link and there is an impulse noise of 1 microsecond. Now I leave it to you to determine how many bits are going to go in error here. If the transmitting and receiving devices are not matched in terms of impedance, this is going to cause performance degradation in terms of reduced accuracy. If the connections between the devices or between the wire and the end device are loose, this is going to result into the packets getting lost, contributing to the overall degradation in accuracy. The failure of devices itself, the noise which is either present in the background or is due to an electrical machinery in the premises of the communication channel. As an example, we see that on wide area networks, the bit error rate, which is usually given for different transmission media, varies between 10 to the power minus 5 to 10 to the power minus 11. You can interpret it in a simple way that 1 out of 100,000 bits is in error, or 1 out of 10 to the power 11 bits is in error. The latter is of course a fairly accurate system. In terms of LANs, the accuracy requirements are spelled out in terms of erroneous frames per a million bytes. As you can see here, that the number of frames are going to be determined by the frame sizes. In more frame sizes or larger frame sizes imply that we would actually be seeing less frames in error and vice versa. in terms of channel access protocols, on shared Ethernet, the likelihood or probability of collision increases, and this degrades the accuracy. These collisions can be categorized according to the severity. For example, if the first 64 bytes collide, this is termed as a legal or runt frame. So this collision is detected and then the transmitters back off and then retransmit again. The typical acceptable value is 0.1%. It means of 1,000 frames transmitted, only one frame could actually suffer from collision. It is important to make a point here that late collisions are illegal. Late collisions means that frames of very long sizes collide in such a way that not only that their headers collide, their main body carrying message also collides. Let's look at a simple mathematical expression that was given in this paper titled Validating an Architecture Simulator. In this paper, accuracy has just been defined as the ratio of the real value minus the error divided by the real value expressed as percentage. Of course, it's a very simple expression, but the key is that this expression would be tailored and affected by the frequency of errors that we have just discussed at various layers in the transmission media and at the devices. So the frequency of events plays a key role in the overall accuracy. Now, in order to use that expression that we have seen, the error computed would now be dependent upon the frequency which these errors occur. For that, this expression holds. The error is equal to the summation from I equal to 1 to n for the event E sub I in a system, and its frequency is multiplied with the difference of the real and simulated values of the costs which are borne in terms of transmission. So real EI is the desirable cost of the system, and simulated EI is the obtained cost of the system. If these two are exactly the same, it means the system is 100% accurate and it is behaving the way it should be.